Hello everyone, welcome back to ECE350 again. This is lecture 14. In this lecture, we're going to talk about your transformer and motional EMF. Remember the last lecture we talked about transformer EMF. We're going to talk about motional EMF in this chapter, in this lecture. So, what transformer? What are the transformer applications? You can name few. All the power system out there, they use transformer from generation all the way to your household, and also an electronics device you buy, they have small transformer in there, and also like your microwave inside your house, they have a transformer there, so magnetron, and so on. The transformer application is everywhere. We would not see them because it's always covered by a nice cover. And there are high power and low power transformer. High power transformer used for power system, and low power transformer used for basically communication circuits. And size versus frequency, we're going to talk about that too, right? So transformer, ideal transformer is basically your current and voltage of two different sides, side one, side two, depends on your transistor, because the amount of voltage you induce is depend on how many turns you have in that particular side, right? So this side one depends on n1 turns, side two depends on n2 turns, and if you put it together, there's the equation right here. And if you with the current, that's right here, because you cannot produce the power is same, so V1 I1 equal to V2 I2. There's no power difference between two sides. We're assuming ideal transformer, so there's no power loss. All right, so that's why your V1 over V2 would be give you I2 over I1, and that is changes over here, right? And you can also go, you can transfer the impedance from one side to another side by using this simple equation here. So this is input side, this is the output side. If you try to transfer everything to the input side, you just need to use the transfer square and multiply the impedance on the other side. All right. So also you can verify the direction over here. So for example, your I2 direction is going this way, right? It's going this way, right? So what happening here is that your flux coming from here. This is the we call it the BT previously. So that inducing a current here, right? So that current should oppose the flux that inducing. So if you have this current direction over here, so that flux is increasing this way, right? Increasing this way. So that induced flux should go this way, right? It should be induced, right? So to do that, inside the lobe, I'm talking inside the lobe. This is inside the lobe. This is coming this way here. That's a different color. So this is your inside the lobe. This is your BT, right? And inside the lobe, your B induced go up. So to do that happen, four fingers represent the B induced inside the lobe. Look at the thumb. Thumb is current. Thumb is going this way, right? And now if you wind them, this is the winding, the different winding here. If you winding changes, look at what happened. Still your current here, this is going inside the lobe, coming down. It's increasing inside the lobe. Your induced flux should be this way here, be induced. This is the BT, right? So then again, your current needs to go out the thumb. Look at the current going this way and coming down other way. So this is still the current going out, but your polarity changes because current going here in this side. So this is positive, this is negative, and for this one, this is positive, this is negative. So if you change the winding, you can also change the polarity of the transformer. All right. So if we ignore the sign for a second, this is what your voltage induction over here, and if this is your phi max equation, sinusoidal flux, then your voltage induction will be right here. So this is the magnitude right here, and this is the time component. So that magnitude, if you want to find the VRMS, you can divide that by square root of 2. That's your magnitude. So if you look at the magnitude of the voltage, it depends on basically three different parameters: your flux, right? Then your number of turns and frequency. So you can easily see how can you basically maximize the induced flux, and also you can see that what is the difference between frequency and size. We're going to talk about that in the class, and we're also going to show this between the class how transformer works. Again, the same thing over here, so you can also simplify that using this equation over here or this one over here. It's a simplified equation for U1 max and E2 max, induced voltage in both coil. So now, let's talk about the motional EMF. Motional EMF, you have a charge moving with the velocity u in the magnetic field B that force force Fm on the charge would be Q U cross B. It's a cross product. It's both a vectors cross product, right? And also you know that F is Q times E. You have learned them in physics 260, this one here. So then if that equation could be modified, the equation over here, electric field is Fm over Q, that means is U cross B. So now you know that if you integrate electric field over a distance, you get the voltage, right? So there's the next equation over here. So now if you integrate EM over a distance with a dot product, you get the voltage. That means you're integrating U cross B dot DL. DL is the distance, right? So this dot product need to be they need to be in the same direction or not 90-degree angle. If you have 90-degree angle between these two, you get the zero voltage. That makes sense. If you get 90-degree angle between U cross B and DL, you get the zero voltage. So it cannot be 90. It need to be if they're aligned in perfect direction, you get the max voltage. If you have an angle difference less than 90, you get reduced voltage. All right. So over here, U for this particular diagram here, U cross B, U is going in the X direction, right? And your B in the Z direction. So X cross Z will give you negative Y, and U V0, V0 is the U and V0 is the magnitude. Then your voltage induced between 1 and 2 would be negative U B0L. If you now put it back into the equation over here and you do the integration, you get negative U B0L. That's the voltage induced, motionally induced voltage between point 1 and 2 of this conductor over here. All right. So the equation is this one over here for a contour closed. If you have a closed loop contour now, you have a contour here now. All right. So that's the equation. All right. Remember, the only part of the conductor will contribute to the voltage if this is non-zero. If this is non-zero, if that is zero, that does not produce any voltage. So let's put our understanding together here. So we have this ring over here in XY plane. So this is on the XY plane. This one is on the XY plane, and this is the Z direction over here. We know that we need this non-zero. If this is non-zero, that's only time we get the induced voltage, right? Because induced voltage is basically let's see, Vm EMF would be integration of this over L, right? So I need this one non-zero. So what is U cross B over here? So U is in Y direction, B is in Z direction, right? So Y cross Z will give you X direction, right? So Y cross B will give you X direction over here. It's in the X direction, right? So that means we only get a voltage in X direction. X, because X direction, if DL is not in X direction, so let's say X DL is in X direction, right? I will get it's non-zero, right? But if it's in let's say it's in Y direction, right, I get zero. So that means I'm not gonna get any induced voltage if DL is in Y direction. That means, look at here. So this is the Y direction. That's this part and this part, both in the Y direction. So that means these two part over here, this one and this one would not produce any voltage because they're in the Y direction. So only part of the loop in the X direction, that is basically this part and this part over here, they have the non-zero product that will contribute to the voltage induction. So that means 1 and 2 and 3 and 4 will produce the voltage. 1, 4 and 2, 3 would not produce the voltage. We're gonna do the math of this in the class, and also have another problem here. We're gonna solve this problem in the class too. That's all for this lecture. We're gonna see you for the next lecture.